Assalamu alaikum. Today is the 28th lecture of Software Quality Assurance. In the last two lectures, we were talking about and discussing software testing techniques. Broadly, software testing techniques can be categorized as either white box testing techniques or black box testing techniques. And we had discussed different individual techniques that fall into these two broad categories. Today we are going to talk about software testing strategy. As you know, that software testing needs to be planned in advance and conducted systematically. So we need a strategy for this. And if you go through the literature, you can find that a number of different strategies have been proposed. And so it is not going to be very productive if we go and look at and explore each strategy. Instead, if we take an overall holistic view of those strategies, we find that all of them have certain characteristics that are common in them. So we begin our discussion today with those characteristics. The first characteristic of any software testing strategy is that testing begins at the component level and works outward for the integration of the entire computer-based system. And so in the beginning, we talked about as one of the testing principles that testing should start in the small and then go for what we call testing in the large. The second characteristic of any testing strategy is that different testing techniques should be used. The selection of a software testing technique depends on the type of the project, the budget, the time available and resources available. But we should mix different software testing techniques to develop our strategy, to formulate a strategy so that different aspects of or different categories of software defects can be discovered. Also, testing is conducted by two different categories of testers. One is the developer themselves. There are certain types of software testing that is best performed by the developers themselves. And there are others which are performed better by independent or in some cases third-party testers. So a mix of both kind of testers should be included when a test strategy is being built. And there's another thing that is important to highlight, and that is software testing and debugging are two different activities. But any testing strategy must also include debugging effort as part of it. We will talk about debugging in a separate lecture, but at this point I just want to mention that this means the act of finding defects when certain observations of failure have been noticed while testing is being conducted. So debugging actually happens after the testing activity has been conducted. A strategy for software testing must accommodate low-level tests that are necessary to verify that small source code segments have been correctly implemented. Similarly, a strategy must address and include those tests which look at and check or verify the functionality of the overall software product. This is typically done by verifying the presence of or implementation of customers' requirements in the software product. So we already know that software testing has to at least operate at two different levels. One level is the low level testing, and the other level is high level testing, or it's also known as high order testing. The strategy that we are talking about in regards to software testing must provide guidance to testing practitioners, and it must set the milestones for the project manager. This is very important because a strategy would then enable us to set aside a certain amount of time, and it will guide the test developers to allocate to develop and allocate enough test time, enough time to perform software testing. And in that way, it also helps the project manager to monitor the progress of software testing and to monitor the progress of the entire project by looking at and verifying the achievement of testing milestones. This is important because software testing, and especially the high order testing, typically happens at the end of the software development life cycle. And at that time, the pressure to deliver software is building on the management. And typically, a project team is very close to the deadlines that were promised to the customer. And at that time, there is a possibility of taking shortcuts and as a result, not performing software testing completely and adequately. So the strategy must have enough room built into the project schedule so that enough and adequate software testing activities can take place. A software testing strategy primarily consists of 4 kinds of testing. Those 4 elements of testing are: number 1, unit testing; number 2, integration testing; number 3, validation testing; and in some cases, we have system testing. And this primarily deals with when we have system engineering projects. Now you can see the testing strategy on the screen. As I said, that it has 4 components: unit testing, integration testing, validation testing, and system testing. And all of these combined will then have a complete testing strategy, although each one of these testing types will have further detail about what needs to be tested and what techniques need to be applied. Unit testing concentrates on each unit. For example, a component, a class or a module, if you're talking about structured programming, a function or a procedure of the software as implemented in source code. So unit testing primarily deals with the units or modules as we use them in a particular development approach. Integration testing is next, where the focus is on design and the construction of the software architecture. Here we have an individual unit which has been tested, and it is now being integrated with other individually tested units to have a larger component, and eventually an entire system will be composed that way. Next is the validation testing, where requirements established as part of the software requirements analysis are validated against the software that has been constructed. So we have this entire software product integrated, and now we are testing with respect to the requirements, that have these requirements been faithfully implemented as desired by the customer or not. Finally, we have system testing, where the software and other system elements are tested as a whole. And so if there is a component of system engineering in the project, then that also is being tested with at this time. Let's have a little bit more introduction of each of these testing types. First, we will take unit testing. Unit testing makes heavy use of white box testing techniques, exercising specific paths in a module's control structure to ensure complete and maximum error detection. As it was obvious from the discussion that we started with on this topic with unit testing, that since we are dealing with small and low-level testing, it has to be white box testing, because at that level we have access to the control structures, and we are going to test different constructs within that source code, and we are going to test conditions and loops and control flow and things like that. Next in the testing strategy is integration testing. In integration testing, components must be assembled or integrated to form a complete software package. Each of these individual components or packages or modules have to be unit tested before they are integrated. Integration testing addresses the issues associated with dual problems of verification and program construction, because we are integrating and testing at the same time. Black box testing techniques are used in this approach. There may be certain white box techniques also used here, but primarily the focus is on using black box test case design methods to develop test cases at this level. As far as validation testing is concerned, once the software has been integrated, a set of higher order tests are conducted, and validation testing is part of that higher order testing. Validation criteria is established during the requirements analysis, or when the requirements model is agreed upon. We must use, and so the criteria that was agreed upon in the requirements model must be used to perform validation testing. The validation testing provides the final assurance that the software meets all the requirements. That includes all the functional requirements, all the non-functional requirements, the design constraints, the domain requirements, and any inverse requirements that have been agreed upon at that time. And as you can guess, that black box testing techniques are exclusively used to perform validation testing. Let's talk a little bit about system testing. System testing is the last high order testing, and it typically falls outside the boundaries of software engineering and into the broader context of computer system engineering. We perform system testing when the software is part of a larger system engineering project. So for typical software engineering projects, we may not need this. System testing verifies that all elements, that is hardware, people, databases, mesh properly and that overall system function or performance is achieved as desired. And so in most software engineering projects, we would be testing the interrelationship of hardware, people, and databases, but we will not have large-scale system testing because it typically would require that a special hardware has also been developed as part of the project. An example would be, let's say that a new computer has been developed and its operating system is then developed as a software, and that software, that operating system, will primarily run on that new computing hardware. In that case, we will thoroughly perform system testing. But for ordinary software projects which are going to run on the existing hardware and existing operating systems, we only need to ensure that the software runs and meshes properly with the existing hardware, the operating system, interfaces with the people, and the existing databases. So the level of concern with respect to system testing is much more critical when a system engineering project is being developed. Now I'm going to show you the V model of software testing. This is a very interesting picture, and it builds a relationship between different activities in the software development lifecycle. I'll start at the bottom and then discuss the picture, and we move upward. As you can see that coding is related to unit testing, design is related to integration testing, and requirements are related to validation testing. We can also say that the programs or the source code that we developed are tested by unit testing, while the design is tested at integration time or when we perform integration testing, and requirements are tested when we do validation testing. And this picture also shows the relationship that exists between those development activities in the life cycle which can be categorized as development activities like requirements, design, and coding, and their relationship with testing activities, unit, integration, and validation. And it also shows the linkages between different activities in the software lifecycle. This diagram also shows a very interesting thing, and that is if requirements are incorrect, they are going to have an effect on the design and coding as well as on unit testing, integration testing, and validation testing. So this diagram depicts the chain of activities that exists within a software development lifecycle. Let's now talk a little bit about some strategic issues. It is very important that you specify product requirements in a quantifiable manner long before testing commences. And this fact was clearly visible when we were discussing the V model of software testing. And the product requirements include both the functional as well as the non-functional requirements. Also, we need to state the testing objectives explicitly. Why are we performing testing? And this needs to be conveyed to all the people involved in different aspects of test planning, test case generation, or conducting tests. We must also understand the users of the software and develop a profile for each user category. This information can be gleaned from the use cases that are developed as part of the requirements model. And if we look at each use case actor and user, we can develop that profile and perform the validation and plan the validation testing according to the profile of each user, because they are the ones who are actually going to use the software, and we need to think on how they would use the software. We also need to develop a testing plan that emphasizes rapid cycle testing. Instead of conducting a complete testing activity, we should have rapid cycle testing, analyze the results, and make the corrections. This is going to help us in use the resources better. We should focus on building robust software that is designed to test itself. What this means is that software should be capable of diagnosing certain classes of errors. We need to use effective formal technical reviews as a prior filter to testing. That is, software testing should be done after having either formal technical reviews or software inspections. We had a good discussion on software inspections and their importance as a quality assurance mechanism in software development activities. We should also have formal technical reviews or inspections to assess the test strategy and test cases themselves. So when we were talking about inspections, we said that one of the work products that can be tested are the test plans and test cases themselves. So we are saying the same thing here, that the strategy and the test cases that we develop must also be reviewed or inspected thoroughly. And we must also develop a continuous improvement approach for testing process. As you know that every process in software development lifecycle needs to be improved as we gain experience, as we develop our expertise in certain areas, as we get more training, and as we grow in a company, and as the size of the company grows, it is important that our process, our ways of doing things improve. Otherwise, if they don't improve, they will certainly be stagnant and become out of touch. And so improvement in performing software testing is another important strategic aspect of software testing. Up to this point, we have had some discussion on the different testing strategies or different types of software testing approaches that are part of a software testing strategy. Now we will have detailed discussion on each of the testing approaches. So we will begin with unit testing, and then we will carry on our discussion. Unit testing focuses verification effort on the smallest unit of software, program, or source code. The selection of a unit is dependent on the type of development approach. If we are using an object-oriented design approach, an object-oriented programming approach, a unit would typically be a class. But if we are using structured approach, then a unit can be a function, it can be a procedure. The relative complexity of tests and uncovered errors is limited by the constraint scope established for unit testing. And so everything that is achieved by unit testing is limited to the scope of the unit, and that varies with respect to the development approach. But there is an interesting thing that different units which are not dependent on each other can be tested in parallel. That is, if unit A is not dependent on unit B, then they can be tested in parallel. This activity does not have to be sequential. You can see that unit testing requires certain test cases, and the module that is going to be tested has to be tested for interface. That is, its interface has to be tested. Local data structures have to be tested. The boundary conditions have to be tested. Independent paths have to be executed, and error handling paths have to be executed. So we need to develop test cases for all units that are going through unit testing with respect to these 5 areas of concern, or 5 areas that fall under unit testing. And the picture that you are seeing on the screen is just relating or conveying that concept. The module interface is tested to ensure that information properly flows into and out of the program unit under test. That is, the data that we are sending into the component is properly sent into the component, and we receive an output. That is why we need to test the interface. The local data structure is examined to ensure that data stored temporarily maintains its integrity during all steps in the algorithm's execution. Of course, the unit that we are testing has certain algorithmic information in it. And the reason we test that local data structures is to ensure that the information that that particular algorithm needs is stored according to the needs of that algorithm. The boundary conditions are tested to ensure that the module operates properly at the boundaries established to limit or restrict processing. We had good discussion on boundaries in an earlier lecture also. All independent paths through the control structure are exercised to ensure that all statements in the unit have been executed at least once. I would refer you to our discussion on independent basis path testing when we were talking about white box testing. And similarly, we need to ensure that all error handling paths are also tested. It is important because in some situations, testers don't create those test cases which result in errors, or error paths are tested but not all of them, and as a result there may be some surprises if they are not thoroughly checked. And tests of data flow across a module interface are required before any other test is initiated. So you see that unit testing itself is a very important part of a testing strategy, for any testing strategy actually. Common errors found in computation are misunderstood or incorrect arithmetic precedence, mixed mode operations, incorrect initialization. There may be precision inaccuracy and inaccurate symbolic representation of an expression. And so unit test developers must write test cases to catch these kinds of errors and defects. Since they have access to the programs or source code, they can write test cases which catch these kinds of defects. So the test cases that we are talking about must look for errors such as comparison of different data types. This is particularly true for those languages which are not strongly typed. Then you should have test cases which uncover errors related to incorrect logical operators or precedence. One of the problems we have with when we have operators is that the precedence is not clearly defined in the code. Also, if you are dealing with floating point numbers and you're trying to use equality when precision makes equality unlikely, so these are things that the test cases should try to uncover, because these will lead to errors down the road. Similarly, incorrect comparisons of variables, improper or non-existing loop termination. There are certain loops which are written as they will execute always, infinite loops, improperly modified loop variables. So these are the areas, these are the cases or situations which test cases should try to uncover while performing unit testing. Among errors, one of the areas that needs to be tested is error handling paths and how error handling is performed. Sometimes the error description is unintelligible. It doesn't convey the meaning of the error, and so the error messages or error handling, error description has to point to the tester as to what is the cause of the error. There is another problem that error noted does not correspond to the error encountered, and we see that in many software products. Error conditions causes system intervention prior to error handling. That is, proper escalation has not taken place, and before error handling is done, the system takes over the error situation. The exception condition processing is incorrect. Error description does not provide enough information to assist in the location of the cause of the error. And so these are the areas that need special attention while performing unit testing. Boundary testing, also very important, is the last and probably the most important task of unit testing step. Software, as we had discussed before, often fails at its boundaries. Test cases that exercise data structure, control flow, and data flow just below, at, and just above maxima and minima are very likely to uncover errors or defects. Let me say this again, that test cases that exercise data structure, control flow, and data flow values just below, at, or just above maxima and minima are very likely to uncover errors. ये इसको मैं दोबारा दोहरा देता हूँ कि ऐसी टेस्ट केसेस जो कि डेटा स्ट्रक्चर्स को, कंट्रोल फ्लो और डेटा फ्लो के वैल्यूज़ को उनकी मिनिमम वैल्यू और मैक्सिमम वैल्यू से के ऊपर, यानी कि मिनिमम और मैक्सिमम वैल्यू पे, इन दोनों से नीचे और इन दोनों से ज़्यादा पे जब हम टेस्ट करते हैं तो आपको बहुत सारी एरर्स वहाँ पर डिस्कवर होंगी. और जब हम मुख्तलिफ़ टेस्टिंग टेक्निक्स डिस्कस कर रहे थे, उस हवाले से भी उस वक़्त भी हमने ये पॉइंट डिस्कस किया था. सो इट इज़ वेरी इम्पॉर्टेंट to test boundaries at the unit testing also. Unit testing is a simplified or becomes simplified when a component with high cohesion is designed. So you see that the chain that I'm trying to build throughout this course is that all the activities in software development are interconnected. Each of them has an effect on the following activities. So if the components were designed with cohesion and they were programmed with cohesion, it is easier to test them at the unit testing level. When only one function or one concern is addressed by a component, the number of test cases is reduced and errors can be more easily predicted and discovered. So again, that relates to the same concept. You remember the characteristics of testable software that also dealt with this issue, that in order for us to perform good testing, we need to build good software. We need to design good software. We need to develop a good requirements model of the software so that a good design model can be developed. As a result, a good implementation, a good faithful implementation of the design model can be done. And when we are talking about software testing, resonate the same concept, convey the same concepts, that in order for us to have good, effective, and efficient software testing exercise, we need to focus upfront on the requirements model, design model, and implementation, but we also need to plan and prepare for software testing. So let me show you now a picture which gives you an overview of the unit testing environment. Here you have a unit testing environment which has test cases and wants to test interface, local data structures, boundary conditions, independent paths, and error handling paths. And we have a driver which drives unit tests and different modules and stubs so that it can interface and interconnect with other modules. And the results are produced by the driver. This picture shows the unit test environment. Let's now focus our attention on integration testing. A big question that important one that someone can ask is that if all the components work individually, why do you doubt that they will work when they are put together? The answer to that is that the problem, of course, is putting them together. That is integrating them. And this is not a simple problem. Software integration reveals many problems in individually tested software code. For example, data can be lost across an interface when they are integrated together. One module can have an inadvertent adverse effect on another module. Subfunctions, when they are combined, may not produce the same desired major function. And an interesting problem that can happen is that individually acceptable imprecision may be magnified to unacceptable levels. That is, if we have individual components and they produce results which are in tolerable ranges, but when they are combined together, they start producing results which cannot be tolerated or are way out of the range, acceptable range. And also, global data structures can present problems which never existed when components were individually tested. So integration is very difficult and important aspect of software testing. I'm going to show you a picture of how software should look like after it has been integrated. Here you can see how software should look like if it's well integrated. You see that Lego blocks have been used to demonstrate the relationship between individual components of a large software product, and they must fit together nicely, and there should be no gaps and no problems. This is really the ideal software integration that we would want to have in all software products. Integration testing is a systematic approach, systematic technique for constructing software structure while at the same time conducting tests to uncover errors associated with interfacing. So when we combine two individually tested modules, we not only test them together, but we also ensure that both of them get together to form a larger system or subsystem. Individual components have already been tested, and that is a prerequisite of performing integration testing. We would want to have a systematic way of integrating and testing at the same time, but there is sometimes tendency to attempt a non-incremental integration, what we call Big Bang integration approach, where all components are combined together at the same time and then tested. So the entire software product is tested as a whole, and I can assure you that as a result of this, for large systems especially, leaving aside the toy examples, there would be chaos everywhere. And so this is an approach which should be avoided for all real software projects. So we should rather use incremental integration. Integration testing approaches are typically top-down integration, bottom-up integration, and third is sandwich testing and integration. We will discuss each one of them now. Let's now see the top-down integration, in which the top module is tested with the help of studs, and the stubs are replaced one at a time with the depth first formula. This is commonly used formula in trees. So as new modules are integrated, some subset of tests is rerun to ensure regression also, so that there are no integration problems. Now I'm going to show you the bottom-up integration, slide insertion. Here again you can see that there is a difference between bottom-up and top-down, because in the bottom-up the worker modules are grouped into different clusters and they are built and integrated together, and then we have software drivers which are used to test the higher level components. So bottom-up integration approach is that individual small components are integrated first and then they are combined into a larger system. The third approach is sandwich testing and integration. Here both of the top-down and bottom-up integration approaches are combined. Worker modules are grouped into builds and integrated, while top modules are tested with the help of stubs. So instead of going from top to bottom or bottom to top, we go from top to bottom and from bottom to top, and we meet in the middle. There's another aspect of integration testing, and that when we are adding more components using integration testing, we must perform certain regression tests on already integrated components. This will highlight any problems or issues with those components that have been integrated previously. Today, we have discussed in detail unit testing and integration testing as part of software testing strategy. Both of them, that is unit testing and integration testing, are very important part of any testing strategy. Individually, unit tests are very important, and integration testing is very important to build the software product. A lot of research has been done in integration testing. We will take up validation testing in the next lecture, and till then I take leave of you. Thank you very much.